So this is the recap of the properties, what you have earlier seen. Is just recap so that the following examples you should know all these properties. Okay, so shall we I'll go to the first example. So as I told you, I'll be considering the continuous time LTI system. Okay, so this is an example. H of t is e raised to minus 3t u of t minus 1. Now you are supposed to check whether the given LTI system is memoryless, causal and stable. So just remember the properties what you have come to know earlier. So for if the system has to be memoryless, what it has to, like which condition it has to satisfy? If it has to be memoryless, h of tau should be equal to h of tau should be equal to 0 for tau not equal to 0. But is this property satisfied here? No. H of t, whatever is given, that is the LTI system, h of t is not equal to 0 for t not equal to 0. That means what? The system is having memory. The given system is having memory. Next, what about causality? What about causality? H of tau should be equal to 0 for tau less than 0. Now the given problem, h of t is equal to 0 for t less than 0. So you can just observe from this figure what I have drawn. That is the exponential signal what I have drawn. Yes, h of t is equal to 0 for t less than 0. So the given system is causal. Okay, so next let us see the stability. So for stability, the integration of the impulse response, given impulse response of the LTS system should be less than infinity. So you what is the impulse response given? It is e raised to minus 3t, right? So I'm integrating that. So integral from minus infinity to plus infinity h of tau d tau. Now what is given to us? E raised to minus 3t, which is an exponential signal, and that exponential signal is ranging from 1 to infinity because e raised to minus 3t is multiplied by u of t minus 1. Okay, so u of t minus 1 means it will start from 1 till infinity. So the given signal h of t is ranging from 1 to infinity. So have the summation here, which is ranging from 1 to infinity, e raised to minus 3t dt. So if you integrate and substitute the limits from 1 to infinity, you get e raised to minus 3 divided by 3. So you can just take your calculator and find out what is e raised to minus 3 and divide by 3. That quantity is less than infinity. So the given system is stable. Okay, so this is about one example. Let us continue. Yes, this is a second example where h of t is given as e raised to minus 4 modulus of t. Okay, modulus of t. Now yesterday I told you, when you have modulus of t, you have to consider both the ranges t greater than or equal to 0 and t less than or equal to 0, because you have modulus here. So when t is less than 0, when t is less than 0 means t is negative in this side. So when t is negative, if you substitute minus t here, it becomes e raised to minus 4 minus t. So minus minus will get cancelled. So here you have e raised to 4t, which is a growing exponential when t is less than 0. And this side t is positive, right? So if you substitute a positive value of t, that is plus t. So you have e raised to minus 4t when t is positive, that is this side. So you have e raised to minus 4t, which is a decaying exponential. Now check whether this given system is memoryless. Memoryless means what? The given impulse response should be defined only at 0. The given impulse response should be defined only at 0, and it should be 0 otherwise. But you can see that the given impulse response is defined from minus infinity to plus infinity. It is not defined only at 0. That means the condition h of t equal to 0 for t not equal to 0 is not satisfied. So h of t is not equal to 0 for t not equal to 0. That means the given system has memory. Okay. Next, causality. So what is causality? The given impulse response h of t should be equal to 0 for t less than 0. But the given problem is, what does this mean? It is also defined for t less than 0. That means what? The given system is not causal. Okay. Yeah. Coming to the stability. Stability is the integral of the impulse response defined in the range. Okay, should be less than infinity. So it is defined from where to where? It is defined from minus infinity to plus infinity. Okay, so here minus infinity to plus infinity, e raised to minus 4 modulus of t dt. Now this integration I have split into two. One is from minus infinity to 0 and other one from 0 to infinity. Now from minus infinity to 0, what is our h of t? Refer this figure. From minus infinity to 0, what is our h of t? It is 4t. And from 0 to infinity, what is our h of t? E raised to minus 4t. So here I have from minus infinity to 0, e raised to 4t. And from 0 to infinity, it is e raised to minus 4t dt. Okay, so integrate this. E raised to 4t is e raised to 4t divided by 4 and apply the limits from minus infinity to 0. And here e raised to minus 4t, if you integrate, it is e raised to minus 4t divided by minus 4. Okay, apply the limits from 0 to infinity. So if you simplify this, you will have half. So you can verify this. Take your calculator and you can verify this. So you get 1 over 2. So 1 over 2 is less than infinity. So here we have checked for the stability condition. The stability condition, the integral of the given impulse response of a LTI system should be less than infinity. Yes, 1 by 2 is less than infinity. So the given system is a stable LTI system. Okay. So this is another example. So you can see here, I have 2 into u of n minus 2 into u of n minus 1. Now if you just plot it, you can just see, you can just plot and check. U of n means what? It will start from 0 till infinity. The value of the signal, that is the amplitude of the signal, is 1 because it is a unit step. And you have another signal, the shifted version of this unit step, which is starting from 1 to infinity. Okay, and this is multiplied by 2, and u of n minus 1 is also multiplied by 2. Okay, so u of n is starting from 0, u of n minus 1 is starting from 1. So when you subtract these two, what is that you get finally? You get only one sample at 0, which is just 2. Okay, now you have to check whether it is memoryless or causal or stable. Yes, memoryless. What is the condition for memoryless? The given impulse response should be defined only at 0. That is only at n is equal to 0. Yes, that condition is satisfied. So you can check from this plot, h of n is 0 for n not equal to 0. Means it is defined only at n equal to 0. So the given system is memoryless. It does not have any memory. And causal. Causal, the given impulse response should be equal to 0 for n less than 0, this side, left hand side. So your h of n is equal to 0 for n less than 0. Okay, so the given system is causal. This condition is satisfied. Now stability. Stability is summation of the impulse response for the defined range should give you an answer. It should give you a value which is less than infinity. Yes, but here whatever is our impulse response, you have only one sample, right? So we don't need any summation here because I have only one sample. So it is just 2, which is less than infinity. So the given system is stable. Okay, so I hope, so based on the conditions for the different properties, so given the discrete time LTI system or a continuous time LTI system, you are able to check whether it is having memory or it is memoryless, whether it is causal or non-causal, whether the given system is stable or it is not stable. Okay, now with this I'll be giving you an assignment. So this is an assignment where I've given you 5 impulse responses, the simpler ones. Now you have to solve this. You have to check whether each one of the system is memoryless, causal and stable. Okay, now coming to the next part of the LTI system, that is step response. Okay, step response of a LTI system. Now what is the step response of a LTI system? You know what is a LTI system. What is an LTI system? A system which is both linear and also time invariant. This is an LTI system. Okay, so this is an LTI system. So what is a step response of a LTI system? To define step response, you just recall how did we define the impulse response. What was the impulse response? Impulse response is the response of a system for the impulse input. That was impulse response, right? So based on the same thing, we'll be defining what is a step response, but we define this step response for a LTI system. So I can say step response is nothing but response of a LTI system for a step input. So you know what is a step input? U of n. Okay, so what is that U of n? U of n is equal to 1 for n greater than or equal to 0, and it is 0 for n less than 0. So how does this LTI system responds for the step input? That is called as the step response. Now, why actually this step response is important for an LTI system? Because this response is going to characterize how the LTI system is going to respond for sudden change in the input. Because your step input, you can just observe the step signal from minus infinity. From minus infinity it will be 0 as you keep on increasing the n, and suddenly when n becomes equal to 0, there is a sudden rise in the step signal. So from n equal to 0 onwards it will become 1, and for lesser values of n, that is when n is less than 0, it is 0. So there is sudden change in the input. So how does the LTI system respond for sudden change in the input? That we can analyze if you are able to find out the step response of a LTI system. Okay, so let us see how to find out the step response. Okay, so here I have taken a LTI system. Okay, this is your LTI system. Ooh. Where h of n is the impulse response, x of n is the input, and y of n is the output of the LTI system. So what is the output of an LTI system? What is the output of an LTI system? It is nothing but the convolution of x of n and h of n. Okay. Now in this we have to find out what is the step response. Step response is In the same expression, if you substitute x of n is equal to u of n, then your y of n becomes equal to s of n, where s of n indicates it is a step response. So I can say S of n is convolution of u of n and h of n. Did you all get that? This is the output of the LTI system. Sorry, this is the output of the LTI system. Okay, so the output of the LTI system for a step input. So in this expression, please substitute x of n is equal to u of n. Then the output y of n becomes equal to s of n, which is the step response. So we have step response equal to convolution of u of n and h of n. So mathematically, I'll show you what is the formula for this. Yes, the same convolution expression. This is symbolic representation of convolution, right? Okay, so mathematically, how do you write the expression for convolution? In general, if I have x of n and h of n, we write that as k varying from minus infinity to plus infinity, x of k into h of minus k, right? Okay, now in place of x of n, what you have the step input u of n. So the convolution expression is written as summation of k varying from minus infinity to plus infinity, h of k and u of n minus k. See, this we got by using commutative property. What is commutative property? If you convolve x of n with h of n, or if you convolve h of n with x of n, both will give you the same result, right? Similarly, now here, if you convolve u of n with h of n, or if you convolve h of n with u of n, it is going to give you the same result. So I've taken convolution of h of n with u of n. So the formula becomes h of k into u of n minus k over the summation over the range k varying from minus infinity to plus infinity. Now you know what is the value of this signal n minus k. So what is the value of u of n minus k? It is a step input, right? Yes, whose value is 1. When it is 1? When k is less than or equal to n, it is 1. When k is greater than n, u of n minus k is 0. Okay, so with this, if you substitute this condition, when u of n minus k is 1 for k less than or equal to n, if you take this condition here, then your s of n becomes equal to summation of h of k as k varies from minus infinity to plus infinity. So this is the step response. So I can define step response as running sum of the impulse response for this period, k varying from minus infinity to n. Why only from minus infinity to n? Because u of n minus k is 1 only for this range. Okay, otherwise your u of n minus k becomes equal to 0. So this is the step response of a discrete time LTI system. Now based on this, I can also write the expression for the continuous time LTI system. Same thing, instead of summation, you have to take the integration. So that will be, yes. Similarly, I've written here the expression for the step response of a continuous time LTI system. So S of t is running integral of the impulse response h of tau. So I have to integrate h of tau from minus infinity to t to get the step response of a continuous time LTI system. Now you already know what is the impulse response of a system. Now you came to know what do you mean by the step response of a LTI system. Now you can define what is the relationship between the step response and the impulse response. So you can easily write what is the impulse response in terms of the step response. See, from this formula, it's clear that step response is the integration of the impulse response of a LTI system. So what can be the impulse response? Impulse response will be the derivative of the step response. Okay. So your h of t becomes d by dt of s of t. So this is about the step response. What do you mean by the step response? And what is the step response of a discrete time LTI system? What is the step response of a continuous time LTI system? And what is the relationship between the impulse response and the step response? Now, with this, let us move on to some of the examples where an LTI system will be given to you with its impulse response. Now you have to find out what is the step response for that LTI system. Okay. Yes. So this is the first example. Okay. So what are you supposed to find out? Find the step response of LTI system for the impulse responses given. Okay. So the first impulse response is h of n, which is equal to half raised to n into u of n. So what is this signal? This is an half raised to n is an exponential signal. It's an exponential signal. Okay. And that is being multiplied with this unit step. So when an exponential signal is multiplied with a unit step, your exponential signal will be defined only from 0 to infinity, because your unit step is defined from 0 to infinity. And what type of exponential signal it is? It is a decaying exponential, because this factor 1 by 2 is less than 1. The same is being plotted here. You can just see from 0 till infinity. So it is a decaying exponential. Now recall the formula to find out the step response. So what is the formula for step response? S of n is equal to running summation of the given impulse response, right? So S of n is summation of k varying from minus infinity to n h of k. Okay, what is h of k given to us? H of n is half raised to n, right? So k is varying from minus infinity to n, but our impulse response is not defined from minus infinity to n, but it is defined only from 0 to n, because we have the exponential signal multiplied with the unit step, which starts from 0. So it is 0 to n half power n. Now this you can simplify. This you can simplify if you remember the convergence of this series expression. So last class I showed you the geometric series, how you can convert it, how it converges. So how you can find out the value of this summation. So last class I showed you about the infinite series. Now it is a finite series. Okay. So here this expression exactly remembers this. You can just see when n varies from 0 to n minus 1, a power n, it converges to 1 minus a power n divided by 1 minus a. But in place of a, I have here 1 by 2. And instead of 0 to n minus 1, we have 0 to n. So I can use this, and this converges to 1 minus, instead of a, I have here half, and since the upper limit was n minus 1, you had n here. Now for us the upper limit is n, so half power n plus 1 divided by 1 minus a is 1 minus of half. Okay, so in the denominator you have 1 minus of half, which gives you half. That 2, if it goes to numerator, then the step response S of n becomes equal to 2 into 1 minus half power n plus 1. Okay, so we have found out what is the step response for the given LTI system with the impulse response half power n into u of n. Okay, so try this, the second one. Yes, so this is the second impulse response. It's a very simple one. You can find out the impulse response. Sorry, you can find out the step response for this impulse response given. H of n is u of n. What is u of n? U of n is the unit step which is defined from 0 to infinity. So I've plotted here all ones from 0 to infinity. So what is your step response formula? Step response is S of n equal to running summation of h of k as k varies from minus infinity to n. Yes. So I've taken, since our step is defined only from 0 to infinity, this becomes running summation from k equal to 0 to n. And what is h of k given in this problem? H of k or h of n is unit step whose value is 1. So summation of ones as k varies from 0 to n. It is nothing but n plus 1. Okay, so the step response is n plus 1. Okay, now let us go to the next example. Yeah, so this is the next example. So here you have h of t is equal to t into u of t. What is t into u of t? It's nothing but a ramp signal. Okay, instead of writing h of t is equal to t, both are same. Instead of writing h of t is equal to t, because we know that ramp signal is defined from 0 to infinity. Okay, so t is multiplied with u of t. So finally you are going to get a ramp signal. That is what I have shown here. It is a ramp. It is defined from 0 to infinity. Now you have to find out its impulse response. So what is the formula? You have to find out its step response given the impulse response. So what is the formula to find out the step response?